Hi again, AP Calc students. Here's lesson 5.5, the trapezoidal rule, and we'll also learn about one other rule here. This is our last lesson in chapter 5 and the last lesson of the quarter. So again, thanks for hanging in there during this flipped classroom stuff, and hopefully you're enjoying it, so to speak. Now, we talked earlier in this chapter about approximating area, and remember the first thing we used was rectangles. And we used the program on your calculator, the LRAM, MRAM, RRAM, to approximate area. And we saw that was pretty good, but we did allude to the fact that maybe if we had not just a rectangular region to approximate, especially the area under a curve, maybe if we had something that would follow that curve a little bit better, it might be a better approximation. And lo and behold, here it is. We have trapezoids. So as you can see by this picture here, what we're going to try to do is make little trapezoids that would follow the curve. Now again, it's not going to be a perfect fit because the curves that we look at are not going to be perfect, but in theory anyway, this should be a better approximation. Now let's just review a little bit about how you find the area of a trapezoid. So I'll try to draw one down here. Remember, the area of the trapezoid are the two bases. Now the bases are the sides that are parallel, and then we have this distance here which we call the height, and so that area of a trapezoid, you might recall, was B1 plus B2. We multiplied that by the height, and then we divided by 2. Now let's see how that works in this particular formula for the approximating an integral. Now again, this is an integral. We know how to do it in a couple different ways, using our calculator and also now using antiderivatives, the algebraic way. But again, here's a way that we can approximate using trapezoids. Sometimes we'll actually use some functions to do that, but sometimes we'll have sort of a picture like this where we'll do that. We'll probably do that more in class. Now, we have to figure out the number of intervals. The problem will tell us that. And this h value here, notice what that is, b minus a. So that's your upper and lower bound divided by the number of intervals. Now this y sub 0, that would be this side here. So notice we're actually adding those bases together. We're multiplying in a sense by this height like we are here. There's the h over 2 that we have in this formula here. Now you might wonder why we need all these 2's here. Well, think about it, this y1, this base is actually used for this trapezoid, and then later on it's going to be used for this one. So that's why we essentially have to use this twice, and this twice, and this twice. The only one we don't have to use twice is that very last base of that trapezoid. So that's the formula. We'll use that a little bit in just a second here. Notice this is kind of interesting that the trapezoid rule can also be approximated by taking our LRAM plus the RRAM and dividing it by 2. So that's kind of an interesting aside that's related to this. Now here's another area approximation called Simpson's rule, and this actually is based on parabolas. And your book talks about a way that you can find the area of parabolas. I'm not going to really get into it in this video here, but it's where this formula is based upon. And as you might guess, Simpson's rule probably would be even more accurate because parabolas do have that curviness aspect, which in theory anyway should be able to follow the curve fairly nicely. Anyway, here's the formula for that. Again, it's the same type of thing. We're trying to approximate an integral, an area under a curve. We have that same h value where it's figured out in the same way. B minus a divided by n is the number of intervals. That gives us the h value. This time h is divided by 3. Again, that's based on how you might find the area of a parabola. And then here's our various sides here, or our bases. Notice we kind of alternate multiplying by 4 and 2 and 4 and 2 on and on. And our last one then ends up to be just plain y. Now, certainly we don't expect you to memorize this. We would want you to write down the trapezoid rule and Simpson's rule right on your spark chart. Probably will be a problem on the test that will ask you to do this. Now, let's actually try doing a couple of these and see how that works. We're going to start out with a fairly easy example, We want to evaluate x cubed from 0 to 4 using 4 subintervals and the trapezoid rule. Again, let's just graph and see what this function would look like. Oops, I'm going to get a pen going here. So here's my particular function here. And if I graph y equals x cubed, it's going to look something like this. So my intervals then are going to be, I want 4 of them. So 1, 2, 3, 4. It's going to go from 0 to 4. So you can see where the trapezoidal aspect of this would probably come into play. Now let's actually calculate this out. I've used the table up here. This will kind of help me figure out what those y values are when I do the formula here. So here goes. So using the formula, it's going to be t equals, the h value here is going to be, let's calculate that down here. H is that b minus a over n. And let's just see how that works. So b minus a, the b is 4, that's the right endpoint. A is 0, the number of intervals is 4, so I think you can see that this will end up to be 1. So h is going to be 1 in this case. And so I have 1/2. And then I just look at the various y values. Remember, it's y0. So my y0 would be right here. This would be y1, 2, 3, and 4. So it will match up with the particular x values here. Alright, so my first y value is 0, and then remember I keep multiplying by 2. So it's going to be 2 times 1 plus 2 times 8, nice 8, plus 2 times 27, running out of room here a little bit, plus the last one, remember I do not multiply by 2, so plus 64. So actually this is going to end up to be 1/2, and if you add up all that stuff in the brackets there, it's 136, and half of 136 is 68. So that's the actual area under the curve from 0 to 4 using the trapezoidal rule. Now let's compare that with Simpson's rule and see what we come up with. Again, we're going to use the same function here, the same intervals, all that kind of stuff. This time we're just going to use a different formula. My h is going to be the exact same thing. Look back in your notes, it's still that b minus a divided by n. But Simpson's rule then looks like this. I'll use S for Simpson's. This time it's 1/3 based on the parabola stuff, remember. And then we alternate multiplying by 4 and 2. So it's going to be 4 times 1 plus 2 times 8 plus 4 times 27, and then the last one again stands alone, so that'll be 64. So if I calculate this out, that should be 1/3. Adding all the stuff up in the brackets, I believe, is 192, and 1/3 times 192 ends up to be 64. So this is a little bit less area than we saw before with the trapezoids. Which one do you think is correct? Well, the actual area here is, if you do this on your calculator, the actual area, remember there is a place to do that on your RAM program, or we could just calculate an interval, or an integral, excuse me. The actual area ends up to be 64. 64. So in this particular case anyway, Simpson's rule was the most accurate. In fact, it was actually the integral. It doesn't always happen that way, but by and large you would expect that Simpson's rule may be a little bit more accurate than the trapezoidal rule. Again, that's given this we have the same number of intervals and things like that. It doesn't always happen, but by and large it would be a little bit more accurate. We'll be doing some problems like this in class, but thanks for listening, and we'll see you guys then.